Hello learners, welcome to this course on Embedded System Design using PIC16F877 microcontroller. In this tutorial, I will be describing about on how to interface a keypad 4x4 with PIC16F877 microcontroller. So a keypad is an input device. So we can provide an input to the CPU of a microcontroller. So here we are going to interface a matrix keypad which is 4x4, which consists of 16 switches. So here you see a typical keypad with the numbers 1, 2, 3, 2, 9 and 0 and A, B, C, D, hash, star, etc. So altogether we have 16 switches. If I want to connect the 16 switches to a microcontroller, then we might require 16 GPIO pins. Whereas if I use a matrix keypad, we can reduce the number of pins. We can reduce the number of pins from 16 pins to 8 by connecting the switches in terms of a matrix fashion. So that is the biggest advantage of having your matrix keypad. So here if I take this 4x4 keypad, it has 8 lines coming out of it. So it is named as X1, X2, X3, X4. It indicates a row. Y1, Y2, Y3, Y4 indicates the column. At each point of intersection between a row and a column, we will be having a switch. So for example, when X1 interacts with Y1 at this point, so here we will be having a key 1. Same way when X1 interacts with Y2 at the interjunction point, we will be having a key 2. So similarly, we have 16 interjunctions, thereby we have 16 keys in a matrix keypad. So this keypad can be connected to a microcontroller in 3 different ways: normal mode, pull-up mode and pull-down mode. So let us look at the different modes of connecting this keypad to your microcontroller. So first let us take the case 1, pull-up mode. So pull-up in the sense, by default the row lines will be at logic high. So here you can see the connection of a pull-up mode, where you can visualize that row 1, 2, 3, 4 all are connected to a resistor and it is connected to a VCC. So thereby by default this row lines will be at logic high. And there are switches connected at each interjunction of this row and a column. So when we send a logic 0 to this row, and whenever a switch is pressed, we can get a value of 0 along the columns. So thereby a particular key can be identified. So here the important thing in your keypad interfacing is the rows are configured as output, columns are configured as input. So the 4 row line, row 1, row 2, row 3, row 4 are configured as an output. So this signal will be sent by the microcontroller. So usually a logic 0 will be sent in a pull-up mode. So whenever there is a key press or switch activation, then the corresponding column will read as 0. So the columns will be read by the microcontroller, and if there is a 0 along a column, which means that the corresponding key can be easily identified. For example, if row 1 is sent 0 from a microcontroller, if the switch S2 is pressed, then along column 2, the microcontroller will read 0, which means the switch 2 is pressed. It can be easily identified. So such type of configuration is called as a pull-up mode. So here the important thing is the rows will be provided logic low sequentially, and the microcontroller will try to scan the corresponding column to identify a key press. So this is in terms of a pull-up mode. The next mode is your normal mode or a pull-down mode. So in a normal mode, the rows are connected directly to your microcontroller and columns are connected in the input mode. So there is no resistor connected to your rows in the normal mode. So a logic high to the row can be sensed through column 1 if a switch is activated. Same way, a logic low to a row can be sensed by reading a column. When the value is 0, then we can identify the corresponding switch. So that is in a normal mode. In a pull down mode, what happens is the rows are connected to a resistor and it is grounded. So by default, the row lines will be configured as a logic low signal. So from rows, the microcontroller will try to send a logic high. Whenever a switch is pressed, the corresponding column will read a logic high value. So that is what happens in your pull down mode. So the default state in your pull down mode is low. Whenever the switch is pressed, the read value in the corresponding Y is 1. So in a normal mode, there are no pull down resistors. A logic high provided along the row can be read through a column if a switch is pressed. Same way, a logic low provided through a row, and it can be read as a logic low while reading a column. So these are the different modes of connecting a keypad with your microcontroller. So now in this program, what we are going to do is, we are going to identify a key press and the number of times a particular key is pressed. So that is also we are going to record it. So we are going to find which key is pressed and how many times it has been pressed. Whether it has been pressed for single time or multiple number of times, that we try to see it in the way of a LCD output. So here I take a 4x4 matrix keypad. So here it is named as A, B, C, D, 1, 2, 3, 4. So A, B, C, D represents the rows, 1, 2, 3, 4 represents the columns. So A, B, C, D is connected to RD0 to RD3 of PIC microcontroller, and the columns 1 to 4 is connected to RD4 to RD7. So A, B, C, D will be configured as, or RD0 to RD3 will be configured as output pins, and 1, 2, 3, 4 or RD4 to RD7 will be configured as input pins. And depending upon the identification of a key and how many times a particular key is pressed, so those status will be available on the LCD connected to port B of your microcontroller. So here we are going to connect the LCD in a 4-bit mode. And one more important thing with the keypad interfaces, whenever we press a key, a particular key will be identified and the corresponding ASCII value needs to be mapped. For example, here, if I take 1, when this 1 key is pressed, then I need to map this key press with the ASCII value of 1. So whenever the switch 1 is pressed, the ASCII value will be returned. So ASCII value of 1 is 0x31. So that 0x31 will be returned. Same way, whenever a switch 9 is pressed, it should be mapped with the ASCII value of 9. Same way, whenever B is pressed, it should be mapped with the ASCII value of B. So like that, each key is mapped with the ASCII value. So here I show a ASCII table, ASCII chart. So where you can see the numbers are available here. So 0 to 9, it has an ASCII value from 48 to 57, then some special symbols. Then we have alphabets, capital alphabets and small alphabets. So like that, each switch can be mapped with the corresponding character of a keypad. Now let us go to the program and visualize how to do this in an embedded platform. So for this application, we will be using Micro C Pro for PIC as an integrated development environment, where we will be building our embedded C program, convert it into a hexadecimal file. Then we build our hardware circuit using Proteus 8 Professional. We try to put that hexadecimal file onto the microcontroller in Proteus 8 Professional and check the logic of operation. First, let us build the circuit. So here I have constructed the circuit. So where I have taken PIC16F877 microcontroller. So it is connected with the oscillator circuit here. So oscillator is connected to oscillator 1 and oscillator 2. And there is a reset circuit as well connected to the MCLR pin. So by default, this MCLR pin will be at logic high. Whenever I close the switch, it will go to logic 0. Thereby reset operation will be performed. Then I have interfaced the keypad. So this is a 4x4 keypad. So here you can see it is something like a simple calculator. So 7, 8, 9, 4, 5, 6, 1, 2, 3. And we have addition, multiplication, subtraction, division, equal to. So different operations can be performed. It's something like a simple calculator keypad. This is connected to the port D of your microcontroller. So RD0 to RD3 is connected to ABCD, which is the rows of this keypad. And RD4 to RD7 is connected to 1 to 4, which is the columns of this keypad. And we have connected a 16 cross 2 LCD, where I have 2 rows, and each row we can display 16 characters. And this is connected in a 4-bit mode, where we connect D4 to D7 of your LCD to RB4 to RB7 of your microcontroller. Then the register select line is connected to RB2, enable line is connected to RB3. Then we have D0 to D3 connected to ground, and similarly RW bar is also connected to ground. So read-write operation, we are going to indicate that the microcontroller is going to do only the read operation. So sorry, not the read, the write operation. Then VDD is connected to a supply, and VSS and VE are connected to ground. So VE is for contrast adjustment, which indicates here I am connecting it to a ground, means I am going to have a high contrast. So once we build the circuit, let us go to the program and build the embedded C program. So this is the program where you can see I have selected PIC16F877 microcontroller, and the oscillator frequency is 20 MHz. So the same frequency should be set in your Proteus 8 environment also. So first we define certain characters, KP, C, count, old state equal to 0, and text of 6 characters. Then I define where I have connected the keypad. So keypad, I have connected it to port D. So we have connected the keypad, 4x4 keypad to port D. Then we define the LCD connections. So LCD RS, register select line, is connected to RB2, enable line is connected to RB3, D4 to B4, D5 to B5, D6 to B6, D7 to B7. Same way the corresponding data direction registers are configured. So RS is mapped to TRIS B2, enable is mapped to TRIS B3, D4 to TRIS B4, D5 to TRIS B5, D6 to TRIS B6, D7 to TRIS B7. So now let us start with the main program. So first let me define the count to be 0. So this count variable is used for providing whether a particular key is pressed single time or multiple number of times. So that count value will be taken. So for example, if key 1 is pressed 5 times, then the count value will be reading 5. So the count variable is used for indicating how many times a particular key is pressed. Then we initialize the keypad, we initialize the LCD, then send the command LCD underscore clear, which means the buffer registers will be cleared. Then we are going to switch off the cursor. Then in the display, we try to put along first row, first position 1, and key in the second row, first position, we put times. So which key is pressed will be displayed on the first row. How many times a particular key is pressed will be displayed on the second row. Then in the main program, first we start with the do while function. So I take kp equal to 0. So kp is for identifying which key is pressed. count is for how many times a particular key is pressed. So first I am going to use this function keypad underscore key underscore click. This will read whether a particular key is pressed. If a particular key is pressed, then that key value will be sent to the kp variable. So this keypad underscore key underscore click will return a value between 1 to 16. Since I have 16 switches, so it will return a value between 1 to 16. So those values will be put on to this kp. So depending upon which key is pressed, a corresponding value between 1 to 16 will be loaded onto kp. So this operation, this do while will be performed until there is a key press. So until I get a key press, so not of kp. So until I get a valid key press, so this do while will continuously run. Once there is a valid key press, then a value between 1 to 16 will be assigned to kp. Now I need to check that value, whether the key press kp as 1, 2, 3 or it has 16. So from 1 to 16, the kp can have any value. So I want to check what is that value. So for the first switch, what is the corresponding digit I should have? It is 7. Right? So in your display, so this is the first switch. So for the first switch, the corresponding ASCII value to be mapped is for 7. Same way for the second switch, so this is the second switch, the corresponding ASCII value to be mapped is 4. For the third switch, the corresponding ASCII value to be mapped is for ASCII value of 1. So like that, each switch needs to be mapped with its ASCII value. So here you see, if the switch 1 is pressed, then I put kp equal to 55. So why 55? When I look at the ASCII chart, here you can see for 7, the decimal value is 55. So that is why kp is read with 55. So this is a ASCII chart. We are trying to map a corresponding key press with the ASCII value of the character. Same way, when second key is pressed, we put a kp value of 52 because it represents a digit 4. So for 4, the decimal value is 52, which is the ASCII value. So similarly, for each key press from 1 to 16, we put the corresponding kp values. Corresponding numbers, we try to load it. Once we have done, we have identified a key press and we have also mapped it to a corresponding ASCII value. Next thing is I want to know whether my key press is for the first time or it is for the second time, third time or subsequent times. We need to identify. So for that, what we do, we take a variable called as old state. So the old state, initially I have defined it as 0. Right? So now this 0 is compared with your kp. When there is a valid key press, we might have assigned some kp values between 1 to 16 and these values are mapped between the numbers available in the keypad. So I am going to check whether the kp is not equal to the old state. If it is not equal, means the count is 1. So the switch is pressed for the first time. For example, let us take, when for the first time I have pressed switch 1, so it is mapped to the ASCII value of 55, 7, ASCII value of 7, which is nothing but 55. So now I check 55 is not equal to 0 because initially old state I have set it as 0. So 55 is not equal to 0, which means the count value is 1. So the switch 7 is pressed for the first time. And I try to update the old state. So now the old state becomes 55. When again the same switch is pressed, when again the same 7 is pressed, I will get kp value as 55. So now when I check kp 55, whether it is not equal to 55, no, it is equal. So in that case, this statement will not get executed, it will go to the else part. In the else part, I increment the count. Now initially the count was 1, now it will become 2 because this is the second time the same key is pressed. So like that, the subsequent number of key presses can be easily recorded. Once I get the count value, I can display this count value onto the LCD. First, in the first row, 10th position, I put the key value, which key is pressed, and I am checking whether my count has reached 255. If my count has reached 255, because count I have declared it as a character variable, so we can go up to 255. Once the count is exceeding 255, I can reset the value to be 0. Else, if the count value is not 255, I can convert this count into a string using the word to string function and then put that value onto the LCD in the second row, 10th position. So in the first row, 10th position, it shows which key is pressed, and in the second row, 10th position, it shows how many times the particular key is pressed. So that is how this program identifies a key press, and it also keeps a track of how many times a particular key is pressed. Once we have done with the program, let us compile the program by building the program. So once building is done, it will create an hexadecimal file. So we will go to the Proteus environment, load that hexadecimal file, right click on the microcontroller, edit properties, select the hexadecimal file. Okay, so the hexadecimal file is keypad_LCD. Select it, then put the oscillator frequency. We have set it to 20 megahertz. So processor clock frequency is also set to 20 megahertz. Okay. Now let us check whether the program is working fine by pressing the play button. Now it shows key times. It is waiting for a key press. So if I press 5, we can see the key pressed is 5, and how many times it has been pressed? 1 time. If I press the same key again, 5 for the second time, you can see now the count has increased to 2. Same key is pressed for the second time. If I again press it, you can see the count value is increased. Next time, again count value is increased. If I press some other key, 9, you can see now the key is 9 and it is pressed for the first time. If I press it again, it is increased to 2. So by this way, we can easily interface a keypad to your microcontroller, and we can identify which key is pressed and how many times it has been pressed. So this type of interfacing your keypad with a microcontroller will help in designing a simple calculator. We can also expand this for interfacing your keyboard with your microcontroller. So in this tutorial, I have discussed about on how to interface a keypad with PIC16F877 microcontroller. Thanks for watching. Please subscribe for more technical learning. Thank you.